Okay, we're moving on. We've talked about weather in general terms and about the atmosphere in general terms. We're going to take a look at something more specific now. So where does the energy to make the atmosphere run come from? Everything needs energy to make it go. So the atmosphere's energy comes from the sun. So in order to understand weather, we've got to understand something about how that energy gets here and how it works when it gets here. So this chapter can be a little bit complex. So we'll see how we do with it here in a minute. So the key thing here is we're dealing with electromagnetic radiation. You see it outside when you can see with your eyes something visible. That's electromagnetic radiation. Did you know that you listen to a radio wave? A radio or a TV, that's electromagnetic radiation. So all of that is some form of electromagnetic radiation. And say you microwave something, you heat it up with electromagnetic radiation. And guess what? The sun heats us up. And these are the different spectrums. You can see AM broadcast here are like 1 kilometer wavelengths and all the way down here to the visible and then ultraviolet and gamma rays and X-rays. All different varieties of electromagnetic radiation. So what the heck is it? One of the interesting things about it is, too, it transmits through space or even through materials. It doesn't matter. It just moves right on through if there's a vacuum in space. So a wavelength is the distance between two wave crests. Think of it if you're in the ocean. One wave breaks over top of you. The length between till the next wave breaks over top of you is a wavelength. So you have the two high peaks and one valley. Frequency is just how many of these peaks are passing you in a certain amount of time. So if you're in the ocean, I know when I get hit with a lot of waves, one after the other, and that is a very short wavelength. A lot of times boaters have trouble in the ocean because the wavelengths are so short. It makes them bounce all over the place and they don't do as well. The interesting thing about electromagnetic radiation is it moves at the speed of light. So it's 186,000 miles per second or 300,000 kilometers per second. And all electromagnetic radiation moves at that speed. So if the wavelengths are shorter, there's more energy. If the wavelengths are longer, there's less energy. Everything is a black body to somewhat of an extent. That's why when you look and use nighttime vision goggles and you see a person, they're emitting infrared radiation back, it's a black body. We're all black bodies to some extent, just some more than others. So at a constant temperature, all radiation it absorbs in a black body, and everything that it receives, it re-emits in some other wavelength. A true black body is a perfect absorber and a perfect emitter. So there are some things that govern that too. And yes, the sun and earth are very close to being black bodies. So one of the interesting things, there's something called Wend's displacement law. What it says in simplest terms is that the speed constant is over top of the temperature gives a wavelength. All right. Earth's temperature, we'll say in absolute is around, 25 degrees Celsius. So C divided by 25 would be one wavelength. Sun's temperature, a little different. It's like 190,000 Celsius or more. So think about it. Wavelengths are going to be a lot shorter the hotter the object. And that's why the sun is putting out ultraviolet wavelengths and the earth is putting out infrared, or you as a person are putting out infrared radiation. Stefan Boltzmann law, interestingly, whatever the temperature of that body is to the 4th power. So it's like if the sun was 2 times 2 times 2 times 2. Or, in the sun's case, maybe that is 190,000 to the 4th or whatever. It is a huge number. So the power from the sun is way more than the power that comes out of the earth. Interestingly, when you look at the inverse square law, the further we are from the sun, by a radius from the sun, every time you increase that, you square it. So say the radius is 3 times further than the earth. So it would be 3 squared would be 1/9. So the amount of radiation that reaches that planet would be 1/9. If it was 4 times, it would be 1/16. All right. The sun doesn't come in at a nice, simple, direct angle. If you look at a flashlight, you see that if you put it at an angle instead of straight up and down into an area, it covers a larger area. In other words, the amount of electromagnetic radiation is spread out over a larger area. Even though it's the same amount that came in directly down, there's going to be less of it because it's spread over an area. So any visual spot on that area is going to be a little bit less. The Earth does the same thing. The Earth is at a tilt to the sun. So as we're going around, the sun may be hitting it right on the equator at an equinox, at the spring or the fall equinox. It is considered exactly at the equator. The sun is literally passing the equator at that moment in time. So it has perfectly, in most intense, like a sun spotlight of radiation, spotlight of flashlight looking in, right intense right at the equator. However, at the poles, look at it. The angle is a lot different. It's going to be spreading out. There's not going to be that much radiation reaching that angle. So the most intense solar radiation is going to be where the sun is directly overhead, which is always between the Tropic of Capricorn and the Tropic of Cancer. Somewhere in that area is the sun is going to be directly overhead. It does not get directly overhead up here. So we're always getting less radiation. And you can see it here by the amount of radiation in the wintertime. Look at Antarctica. There's no radiation whatsoever in their winter. Whereas Massachusetts has a fairly Brookport in New York has a fairly up and down curve. If you're in Singapore, which is very close to the equator, you don't see a whole lot of change. And here is that tilt. Wintertime. We're in the northern hemisphere. Notice how it's tilted away from the sun. Summertime, we're tilted towards the sun. That Earth never moved and changed that tilt. That tilt was always the same. It just rotated around the sun. So now all this radiation has to be done something with. So what happens to it? Well, it can be absorbed by the Earth, or it can be scattered away or reflected. And somehow all of that must be 100% of that total amount of radiation we just received from the sun. What's scattering? Well, think about it. When there's really thick clouds over your head, it seems kind of dark, doesn't it? Well, what happens is the top of those clouds are scattering the sun's radiation. Some of it is coming through, you can still see, but a lot of it is being transferred somewhere else. That's scattering. Reflection is something very similar to scattering. It's like if you had ice and clouds. They reflect. They have a high albedo. In other words, the sun hits it and goes right back, all that electromagnetic radiation right back towards the sun. If you're in the wintertime and you've had a fresh snowpack, if you ever look outside, you don't exactly see very well. It's so bright. That's because of the high albedo. Absorption does occur, and it converts the radiation then into heat energy. Some of it's into the ground. Some of it is absorbed in the stratosphere by ozone. That's why the stratosphere warms so much. One of the interesting things, if you look at a satellite picture, you can see the snow here. The lighter the surface, the higher the albedo. So the closer to white the surface is. Now here is the actual planetary albedo. The Earth system basically reflects about 30% of the solar radiation received. 23% is absorbed by the Earth atmosphere, and another 47% by the planet itself. So that is the general radiation budget. All that energy that has come into Earth, that's what's happened to it. Now we got to account for all that. So since the Earth is recipient of that, you can see it in the profile here. A lot of the Earth's energy in the stratosphere is absorbed and made into heat there. And that kind of protects the Earth from some of the ultraviolet radiation from the sun. But there's got to be a global equilibrium. So the amount of solar radiation reaching the Earth has to be balanced by the infrared radiation emitted into space. So with that, and if it wasn't, the temperatures on the Earth's surface would be continually rising. But they're not. Relatively, we are fairly uniform if you look at it as a large picture. Greenhouse gases. Okay, when the sun's radiation hits the Earth, and remember the Earth acts as a black body, remember the Earth also is a lot cooler than the sun, so its wavelengths are more in the infrared range. So a lot of greenhouse gases do not absorb ultraviolet radiation, which is the sun's radiation, but they do absorb infrared radiation. That's what makes our planet habitable. If we didn't have greenhouse effect, our planet would not be habitable. It keeps the temperature where it's at. So they absorb a lot of the visible radiation, and infrared radiation is absorbed by greenhouse gases. So what are some of the principal greenhouse gases? Guess what? Water vapor is a big one. Then carbon dioxide, then ozone and methane. Each one contributes to absorbing that infrared radiation coming back from the Earth towards this out into the atmosphere. And then when it absorbs it, it retransmits that radiation. Part comes back to the Earth, part goes out into space. So think about the Gulf Coast versus the Southwest U.S. We'll look at humidity first. So if you go into the Southwest U.S. where it's very dry, desert-like, there's not a lot of water vapor. Sun strikes the ground, heats it up, and during the day the temperature rises because the sun's coming in. But at night, there's nothing to stop all that infrared radiation from being transmitted back into space. Water vapor just doesn't exist much there. So most of that is cool. It really cools off very quickly. Now, let's take the Gulf Coast or somewhere when it's really humid at your house. There's a lot of water vapor there. So what happens is during the day, yes, it's heating up, similar to the desert, maybe not as much, maybe more clouds reflecting some of the sun. But at night, what do you notice is it's a lot warmer. Why is that? Because that infrared radiation is being absorbed by the water vapor and then transmitted back down to Earth. So that keeps the places that are more humid warmer at night and keeps temperatures higher. The calendar effect is just a way of measuring with using the Keeling curve of basically your carbon dioxide in the atmosphere. It doesn't take into account all greenhouse gases that may contribute towards the global warming that goes on. And one of the interesting things is with CO2, you can notice it spikes during the wintertime. During the summertime, CO2 is absorbed by more plant life, so it is more of it's absorbed, used to make oxygen. So with that, I just wanted to show you one last thing here with all of this. Here is a satellite picture. It's the whole globe from the East Coast visible satellite. Here is sunset. Notice that in the southern hemisphere right now, the sunset is further to the west than it is in the northern hemisphere. That's because we are tilted towards the sun, so that the sun is hitting more directly up here and making it brighter in the northern hemisphere and staying light longer. One of the interesting things about GOES satellite is there's a lot of channels. What do I mean by channels? Well, if you look at bands, there are actually 16 of them. Why did we do that? Well, each one can see something different. I'm showing you a visible. Say I wanted to look at infrared that basically is coming off vegetation. Or let's look at infrared that was coming off some cirrus, some high-level infrared. And you can see here, there's some high cirrus clouds. We're not seeing any infrared now, however, down low. We're looking at all the high cloud tops, and we're seeing it. Say I wanted to look at water vapor. Water vapor is a greenhouse gas. It's absorbing it. So let's just take a look at water vapor channel here. And you can see the water vapor all over the globe. You can see a lot of dry air down in here in this parts of the world. A lot of wet up by us and across the tropics right here. So pretty cool stuff. You can actually see all of what we've been talking about by using instruments that are on a satellite. So hope you got something out of this, and let me know if you have any questions.